Okay, let's get started. So I need to make a little correction from last time. So T cylinder of W is the 2 pi L squared TPL Z squared minus 1 over 24. So that's the coming from Computational Ratio. And this one coming from Schwarzschild derivative. Okay. And then so we substitute 2 pi L Ln plane to z to the minus n minus 1 over 24. So therefore, so Ln cylinder, this can be written as 2 pi. Yeah, most of people already noticed from the WeChat. Cylinder e to the minus 2 pi I and W. Okay. And then last time I think I missed. Sorry, no I think. I missed minus sign here. Last time I missed minus sign here. So be careful about here. And also Ln cylinder is Ln plane up to correction of the delta and zero. Okay. This is this. Okay. So this is a correction I need to make. And also I made a mistake for the last time. So cylinder is equal to 1/2 A0 squared plus product sum of A minus n and n minus 1 over 24. And last time I missed this time. So the correction is the here, correction is here, and the correction is here. Okay. Yeah, and then so last time I couldn't answer the question to why the vacuum energy is measured by cylinder. So cylinder has the spatial direction is length L, whereas the for complex plane, so you cannot you don't have a definite length. I mean, as you change the circle, the length will change. So therefore, the state is defined by circle at the circle via radial quantization. So therefore, since there's no you go to infinity, so therefore you cannot define the vacuum energy will define only when the vacuum energy is 0. On the other hand, here on the other hand, here vacuum energy is indeed given by 2 pi L square minus 1 over 20. So you have a definite length here. Since this has a definite length here, you can define the vacuum energy. Okay. So this is what I couldn't answer last time. So here, the radius is not well defined. So it's the bicular is 0. Is well defined. Okay. So, and then we move on to pre-Fermat. And we know that the so we know that the T. So we start with the T of V minus 1/4 psi of V, and then psi V, psi W is indeed 1 over Z minus W. Okay. So this is the OPE of the two primary fields. So, and we know that T of Z is equal to 1/2 psi of W. Sorry. OPE of stress energy in terms of psi of W is indeed 1/2 So therefore, this is the primary of the compound dimension is 1/2. Okay. So this is what's really happening. And then, so in the homework, so TW is indeed plus 2TW Z minus W square plus partial T of W Z minus W. Okay. So this is the if you do the honest computation of by using this one, I mean, so you just have like a minus 2W then you have the yeah, so either this way and this way to get the highest or this way, sorry, and this way to get the highest singular term, like, yeah, most singular term. And you have to be careful about the swapping ferment. If you swap the ferment, you get the minus sign. Okay, so you need to be careful about this one. Okay, so that's then you will get this one. So therefore, for free ferment, central charge is equal to 1/2. Okay. If the series is hollow, non-chiral. Non-chiral means left moving sector and right moving sector are the same. Okay. So now, so we want to do the model expansion. So model expansion, psi x plus L is equal to psi x. In ferment, so we now if you consider a cylinder, put this free ferment on the cylinder, then you have the you need to impose the boundary condition once you move around here, and this is usually periodic boundary condition. And also you can, for ferment, you can have the other boundary condition. Okay, you can have the other boundary condition. So that's called actually spin structure. Spin structure. So you can have either, if you have a non-trivial, how to say, one cycle. This is called one cycle. So the first homology group, you can have either periodic or anti-periodic boundary condition for Fermi. Okay, so you can have minus sign, and this one is called Ramon. This is called Levy-Schwartz. Historically, this is called, this is called bounded. And sometimes condensed matter people use this is bounded spin structure. This is unbounded spin structure. Whichever you call it. So this is Ramon and it's Levy-Schwartz. Psi. So then we can have a mode expansion if you impose this boundary condition. Yeah, so the W is indeed equal to T minus Ix, as far as I remember. So this is X direction, this is T direction. And there's a subtlety appear here. So to have the periodic boundary condition, the K has to be integer. Otherwise, if you impose Levy-Schwartz for cylinder, you have K is half integer. Okay. Huh? Okay, so that's what's really happening. Do I make a mistake? Just tell me if I make a mistake, since it's recorded. Yeah, I think it's okay. Then you can do the compound translation to the cylinder. Sorry, complex plane by Z is equal to e to 2 pi W over L. E to 2 pi W, I already forgot. What is the correct over W? Over L. Then you can have the following mode expansion. Sorry. Before then, I have to quantize them. Sorry. So now psi is the operator. So now this mode B is the really operator. So therefore, we have to do delta. So this is the really the canonical computation ratio. Canonical anti-computation ratio. Is given by here. So now here is anti-computation ratio. Okay? Instead of so this means the BK BL plus BL plus times BK is equal to delta function. So that's what's going to happen. And then as before, so we can have a vacuum. So the Vk, when k is greater than or equal to this annihilation operator, B0. So and the Bk is equal to 0, and the Bk is the creation operator. When k is less than 0. And then if the Ramon sector, you have a there's a B0, which is called 0 mode, which becomes important later. zero mode. This becomes important. Okay, so this becomes important. Later, so we'll see. Size cylinder of Z, W, is mapped under this computational transformation. Like side plane of Z is equal to L over by computational transformation. If you do the computational transformation cylinder of Z, which can be understood as the Z is equal to e to the 2 pi w. So then, so this factor coming from really the, since psi is the primary field, so you have the factor minus over half for component transformation. So this is the component transformation. Therefore, this factor will give rise to this prefactor. So now, so we have the square root of 1 over z here. So now, so therefore, model expansion will become slightly different. Psi of z become like this way. Of course, the k equal to 0 corresponds to so nu equal to 0 corresponds to, so here. So therefore, here nu equal to 0 and nu equal to 1/2. But however, since there is a minus 1/2, which is conformation of the 1/2, so therefore you can have the, if you identify the circle, so if you try to identify the boundary condition, once you move around 2 pi, you get the boundary condition becomes the opposite. So namely, psi of z psi is the so the sign becomes the opposite due to this minus 1/2 shift. Okay, that's what's really happening. So now we can see the 2-point function. If you have the two-point function psi of z, which is the model expansion by using plug that this model expansion vector in here, you have the for so Navier-Schwarz is very simple. So this is an S sector. Okay, so this is the two-point function, and then you can apply this computational ratio here. Okay. Computational ratio here. So namely, so you can just swap creation annihilation. So it becomes creation and annihilation operator. You swap that, then it will give you the some non-trivial constant when k is equal to plus q is equal to z. Okay. So the most important part, the non-trivial part, is this part. most important coming from here, and then what you're going to get is the essentially here sum over k and q z plus 1/2 z minus k minus 1/2 w plus k minus 1/2. Sorry. So I think I should write like this. Okay. So that's what's going to happen. And then of course it has to be it has to be k has to be greater than equal to 1/2 plus positive non-negative integer. Okay. So that's what's going to happen. And then this, so you can easily compute this one, which is 1 over, if you do the geometric series, w. Okay. So this is what's going to really happen. Okay. Really geometric series, which means that this is equal to, you can just check 1 over z, 1 over minus w over z, which is the 1 over z, 1 plus wz, plus squared and so on. Okay? So that's what's really happening. Which is equal to this one. So since this is a half integer add up to half integer becomes integer. Okay? So this is the Navier-Schwarz sector. So here, computation, everything in this sector. So you have to be careful. So if you treat it with Perlman, you have to so everything in the Navier-Schwarz sector. Okay. So let's do the Ramon sector. The computation is also the same, but so this can be guessed from OPE of. So we know that the psi right. So we know that the OPE of psi z and psi w is 1 over z minus w. So therefore, two-point function is 1 over z minus w, which can be guessed from the OPE. But Ramon sector is a situation sector, slightly different. You have to do the same computation. It's just over there. So now it becomes this one. And the question is what's going to happen for k equal to 0 equal to q. Okay? So now you guys are a bit look like silent today. So k equal to q equal to 0, it will give you the z minus 1/2, w minus 1/2, and b0, b0. Okay? And since we know that the computational ratio coming from here, so b0 square is equal to 1. Okay? So therefore, so this will give you 1/2 z minus 1/2 and plus sum of k equal to 1 to infinity z minus k minus 1/2 k minus 1. Okay. So this is the case, and you can do the again the same geometric series. So at the let's see. So geometric series will give you the following. So let's do them step by step in that case. So this will give you 1 over what I'm doing here. Sorry. Yeah, I think this is correct. Right? I think this is correct. Right? Do you agree with me? Yeah? So then, if you compute this one, you will get the following. So you will get the following: 1/2 z over w plus w over z divided by z minus w. Okay, so that's what's going to happen. So therefore, I mean, as you take the z equals to w limit, so they behave the similar behavior. So as you go to z equals to w, this one behave similar to this guy. However, globally it's different. So globally, so there is the difference will appear by using periodicity of on the circle. Okay, so that's really what's happening. And now, so we just try to compute the cosmic energy or vacuum energy. Okay, we have depending, so which depends really on the boundary condition. So T of Z. So here there is a prescription to compute normal ordering is as follows. Minus psi of Z plus epsilon psi of Z so that's what's really happening. And we know that the Formalism short sector, this is equal to minus, so derivative of with respect to W, so therefore this will give you the what would you get? 1 over Z plus epsilon minus C plus 1 over E squared. Okay. So for maybe shorts, this will lead you to 1/2 equal to Z. On the other hand, so this is the what was it? NS. If it is Ramon, so you get minus 1/4 limit plus 1/2 to Z minus W squared. Okay. So this is, if you do an honest computation, so I'm not going to do that. I'm really bad at doing, like you guys know, I'm very bad at computation. So you have to be careful. You don't trust my computation. So you have to always do calculation by yourself. You get 1 over 16 squared. So really, so depends on the boundary condition, the vacuum energy of T of Z will change. Okay, will change. Yeah. Vacuum excitation value of T of Z will change. Okay. This is what's really happening in the energy momentum tensor of the fermion, free fermion. And now, so we just want to compute the Casimir energy. So we will do the same thing as before. So we know that the, so we just need to compute the L0 part of the, and then see, so we know that the L0 of cylinder is equal to L0 of plane minus C over L equal 24? 24? So that's what's really happening. So we need to understand L0 in terms of this mode expansion B and so on. Okay? Do you guys agree? So now, on half Z minus, so you just plug. So we know that T plane of Z is equal to psi partial psi. That's it. Okay. So this is the what's, and the plug this mode expansion already erased, already done. Yeah, mode expansion into there. So then you will get minus Q plus 1/2 and Z. Okay, so you have to always impose normal ordering once you define as operator. So operator defined by normal ordering. Okay. So then again, we apply the same computational ratio as before. Oh, sorry. So this can be just simplified. Sorry, this can be simplified 1/2 sum of N and K. Sorry, this is plus. Okay, so I didn't write down specifically. K and Q is Z plus mu. So plus mu. So at the K plus 2, 1/2 Z minus N minus 2. So that's what's really happening. So therefore, so as you recall, so this can be written as the sum of Ln Z minus N minus 2, N is equal to. So therefore, Ln so this is just rewriting of the mode expansion. And this is quite simple. here, of course, Q plus K is equal to N. So here, Q plus K is equal to M. So therefore, so the L0 is equal to K, V minus K for S. Say okay. And then so 16 so this 16 really come from this 1 over 16 here. 1 over 16 here. So since the really, if you do this expansion, what you get is the so you really see the T of L0 sorry plus L0 Z minus 2 plus okay. So if 0 is, sorry, Ln is greater than n is greater than 0, analyze the right vacuum. If n is negative, analyze the left vacuum. So what's really important is this L0 point. Okay? So minus 2 really comes from here, and then 1 over 16 really affects this constant for Ramon sector. Ramon sector. Okay. So this shift can be computed by using this normal ordinary definition of one-point function of TZ. Okay. So now, so we know that the so we use this one. So vacuum energy is really indeed is given by C over. So vacuum energy indeed given by L of 2 pi of E0 is indeed given by minus C over 12 and the plus sorry, I got confused. What I'm writing here? I think it's yeah, holomorphic part. Okay, it's fine. Plus, okay, minus C over 12 and minus C over 12. Okay. Over so an S or Ramon, and you have 24 minus 24 plus 8 or 1 over 8, which is equal to 1 over 12. So for this is including both holomorphic and anti-holomorphic sector. Okay, including holomorphic and anti-holomorphic. So this is factor of 2 is different. Factor, yeah, 2 different from my lecture note. So I include both holomorphic and anti-holomorphic. Okay. Likewise, you can just compute the vacuum excitation value of T cylinder of Z by using computational transformation. like this way. So sorry. Maybe I should write down like this one. Yeah. And W. And then you can do the same computation. You get the 148 over 2 pi over L square and 1 over 24 2 pi over L square. Maybe Schwartz and Ramon. Okay. That's the indeed. So you can just compare between this guy and this guy. So of course, there's up to factor of 2 is different than normalization factor. So that's what's going to happen. Okay. So any questions so far? So the vacuum energy is really different. Depends on the boundary condition you impose. Any question? E0? It's really coming from this relation. So L0 cylinder is L plane minus C over 24 for homomorphic sector. So therefore, since there's no constant there, so L0 acts on the so here it's of course normally order assumed. So if you take this one, it really see only the constant part. Since constant part for energy Schwartz 0, so you just have a minus C over 12 shift coming from here. Do you understand? So sorry, I think this E0, my definition of E0 is the 2 pi L0 cylinder plus L0 bar cylinder. Okay. Therefore, C minus C over 24 times 2 coming from homomorphic and anti-homomorphic, that will give minus C over 12. And the constant term will affect for the shift here.
So the first term
Huh? It's coming from really Computational Transformation of the CFT. CFT. We know that the so T cylinder of W is indeed equal to I forgot the precise 2 pi over L squared. Minus C over 24. This is really come from Computational Transformation. So this minus C over 24, it really affects the relation between plane and the cylinder element. That's what we learned last time. But for this is generic CFT with central choice C. Okay. So now we are going to talk about Torres partition function. So now we only consider the cylinder or plane. So now we change the base space like 2 torus. 2 torus. So now, so we can just use the whatever lattice to define 2 torus. So, and you just define how to say, top and bottom. So you just identify top and bottom, and then left and right, like this. Then you will get the torus, like this one. Namely, so alpha 1 is defined like this way, and alpha 2 is defined. Alpha 2 is defined like this way. And if you can cut this purple and the orange circle, you get this shape. So this is complex. So now, we just consider. So this is the coordinate is W. So W is identified where N and M. So this is defined as integer. So it's a lattice. Alpha 1, alpha 2 define lattice. And now, so we just consider some ratio. So you can always set that without loss of generality. If you consider only shape of torus, without loss of generality, so alpha 1 can be set to 1, okay, in complex plane. And take ratio, so which is tau is equal to this is a situation we are considering. So we take a ratio between alpha 1 and alpha 2 that define a complex structure. So this tau is called the complex structure of torus, or sometimes it's called modulus. Which define which define in the complex structure, how to say? Which defined in some shape of torus. But however, we can do the lattice doesn't change after doing the following transformation. So if the lattice, so this lattice is defined, can be defined as some vector, beta 1, beta 2, which under the transformation and then also to keep the area, so you have to define the determinant should be equal to 1. So this matrix is called 2x2 matrix called the SR2D. Of course, there is so in some sense, so beta 1 and beta 2 can be defined something like this one. So and then whatever, for instance, beta 1, beta 2 can be like this way. Like this one. under this transformation. On the other hand, so if you take alpha 1, so this means that the torus shape become like this way, can become like this way. Okay. Instead of just taking like this way. Yellow is original one is this guy, but it has the same shape. Okay. So if you take a ratio, you get have tau is go to but if you take the matrix, so this is the modular transformation, or it's called the mapping class group of Torres. And if you take the ABCD as the -1, -1, so it doesn't do anything to complex modules, complex structure. So therefore, so you can consider the indeed this transformation up to Z2. Z2 transformation. Z2 means you identify 1, 0, 0, 1 and the -1, 0, 0, 1. So that's what's really happening. And then the matrix called this matrix is called indeed the T transformation, and this S transformation. And in fact, this SL2Z, so this is indeed called PSL2Z, projected SL2Z. And this corresponds to tau plus 1, and this corresponds to tau goes to 1 over tau. Okay. -1 over tau. So this is the, in other words, the so you have a torus like this way, so the T transformation is just a move to the lattice like this way. Tau plus 1. Okay. Tau plus 1. So S transformation hard to draw indeed. It's hard to draw. It depends on tau, but it becomes something like that. From here, I think the S transformation is something like a depending on the how you take the like this. So this is the S transformation, and this is T transformation. Okay, so that's really what happened. So this, in fact, any element ABCD in PSL2Z can be written by like a sum S to the some power, whatever. T to the some power, S to the some power, T to the some power, and like this. you can always write down it's generated by S and T matrix. Okay. Moreover, so this S curve is equal to 1. I mean, strictly speaking, minus 1, which is equal to same as 1. Is equal to, of course, is equal to 1. The identity operator. Okay. So you can check this is true. So, yep. So now we can consider partition function for on a CFT on a torus. So we use the Hamilton formalism to define the partition function. Is there any question? Yeah. Huh? 1, 0, 1, 1. Yeah, if you define like this way, alpha 2, alpha 1, yeah, that's true. That's true. If you define like this way, yeah, thank you very much. Yeah, if you sort, I mean, it depends on notation. Any other questions? Okay, so now we consider the Torres partition function. Essentially, so we need to do the path integral, but so Torres can be defined as the follows. So now you consider the finite amount of the cylinder. So you have a cylinder and you identify top and bottom. Okay, top and bottom. Then you get the torus. But however, so when you do that, you have to shift. I think I should write down here. So here is tau 1. So imaginary part, a real part, and 1. Okay. So this is what's happening. So when you identify top and bottom, you just instead of going to time direction you have a tau 2 transformation. So you just translate time direction tau 2, but spatial direction you have to translate tau 1. So therefore, and also we use the Hamilton formalism so that the e to e okay. So this will generate the time transition in Euclidean spacetime. So I just do the Wick transformation. T goes to here, IT. Yeah, IT. So that the usually e to the 2 pi I th is the usual Hamilton unitary transformation in time translation. But so if you use the Euclidean coordinate, you get the minus like this. Okay. So then tau 2 amount, and you have to do the translation in the spatial direction. Okay. Yeah, spatial direction also the same. So it's a Euclidean signature, so tau 1 and p. So the signature is a bit different. Okay. And now, so you just need to identify top and bottom. To do that, so we know that the Hamilton formalism, the state to define the spatial direction. So space is defined some alpha, is defined. And to identify top and bottom, so you just identify top and bottom. Okay? So what we need to do is the alpha and sum over all alpha. So this is the partition function you will get, okay, in Hamilton formalism. And this can be understood as the trace of Hilbert space e to the Any question? So this H is Hilbert space. This means Hilbert space. Trace over Hilbert space. Huh? So you have the Hamilton formalism and Lagrangian formalism. So in Lagrangian formalism, the partition function z is e to the all the field phi e to the minus s. Yeah, minus s. So this is the Lagrangian formalism. S is action defined by Lagrangian. But for Hamilton formalism, we just need to do the time translation or spatial for the Hilbert space, and you identify top and bottom. So that's the Hamilton formalism to define the final path integral. Does it answer the question? So here, so everything, you define the torus T2 and T2. Okay? The field here is identified fields here in Lagrangian formalism. Well, Hamilton formalism, you just need to sum over states on the top, sum over states in the for partition function. Or, I mean, thermodynamically, whatever. Boltzmann weight is given by Boltzmann weight is given by e to the minus beta. H, right? Sum over any state, right? All the state. Okay. So this is partition function, right? Boltzmann. It's the same thing here. But you need to identify top and bottom. That's why you get a trace. You need a trace. Okay. Any other questions?
Why would we use P?
P is because we need to translate to spatial direction. So if it is just an ordinary cylinder, it's okay, but you have to translate. This direction is identified like this direction, this place. So it's not simple time translation. It's also, you need to shift, you have to rotate a little bit. Okay, so that's what's really happening. And we know that the Hamiltonian of cylinder is defined by L0 cylinder plus L0 bar cylinder. So, and the P cylinder is equal to I. So this is the definition of Hamiltonian and translation. Okay. Translation. Therefore, so this can be rewrite as trace of H given space. So you're just rewriting Hamilton and the momenta in terms of L naught cylinder. And going back to the plane definition, you have Q. Where the Q is given by e to the 2 pi I. So this is the definition of partition function in conformal field. And we will see that so this can be written in terms of sum over n, h, and h bar, character of h of tau, character of h bar, where the h and the h bar is the in the conformal dimension of state h and h bar. So we will see this. We will see this is the case, and then so this is called character of your solution. And this is multiplicity. So let's go multiplicity. How many states the CFT has the conform primary states labeled by H and H1. Any questions so far? So this part is we will see later, but up to this point, I hope it's okay. Okay, so let's take a break. I think it's a good time to take a break. Yeah. Let's take 10 or 15 minutes break so that we can refresh ourselves. But here, I is here. This is I here. Tau 1, IP. Is it the case? Yeah. Okay, let's try to compute in that case. Are you sure? I disagree. I think this is okay.
This one is I cancel, you give the minus sign, and here you have I.
I guess this one.
This side is my side. Otherwise, here you will have some item.
What? But if you look at this one. Ah, you're right.
This is true and this is
Yeah,
wrong.
this is right. I think you're right. This is correct.
Otherwise, you will get an extra item.
You're right. You're right. Thank you very much.
I don't quite understand why we can write the Hamiltonian of cylinder as L0 plus L0. So I understand on the plane we can interpret this plus this as the generator of dilations, and the time direction is this direction, right? So we can interpret on the plane. This thing is the Hamiltonian. So while on cylinder we can still have this, or we just define it to be this.
But I explained it to you in the chat, right? Did you read it?
You mean the lecture? Oh, you on the in the chat group?
Yeah.
Yeah, but I don't.
Yeah. So yeah, this one.
Okay, so we just yeah, I saw that. So we just define the. So why can't we just directly in the cylinder geometry we just derive the the translation in time. I mean the generator of time translation is this direction, right, in the cylinder. Why can't we just derive the generator, but we turn to the complex plane and we come back to the cylinder?
No, we just did the. We just did this one. So this is the connection. Stress energy density power tone, spatial direction comes from.
Oh, okay.
And then if you do the just residue integral, you will
I want to ask, did we identify the time direction as this direction, not this?
this direction. This is time direction.
Yeah,
Imagine
but-
for a time direction.
But if this is the time direction, I can understand that this is the translation of in the time direction. But this is only this part is the time direction.
But Taurus is the you need to rotate in spatial direction. So if complex edges it's rotated, shifted by time direction. This is time direction. This is spatial direction.
Yeah, but in most time we write the partition function as this. So this is a time direction.
So if you don't define the if the theory defines in some like plane or cylinder and so on, this is true. But we need to it's defined on torus.
But this looks like a translation in the direction of this.
No, this.
Right?
So time direction T2 and then tau 2 and tau 1. That's it.
Oh, I understand.
你相当于把这个 I 修到 P 的话，所以如果这么定义的话，这个 I 相当于是那 H 这儿是基因的一个奇怪方面，就是你这个 I 的凤凰一我知道你就是放在这儿，但是就相当于你相当于把这个，就相当于这种细心的本质就是草系统啊。很奇怪。还是有问题，这样的话，那个 P 前面那个实现但是我从最开始的这个定义呢，一个同样是10的，套一个套一个10的意思就是显然就是后来我们用和个这个数去，所以套一套是10，套一套是10数的话，那你在时间方面那个虚实那个肯定是8个多。对，这个平均的时候是除非你把那个这种不往之前，对的，所以就各种。可牛，最方面的是把那个把屁股啥玩意儿？可以换上。
Oh, by the way, so every time I updated lecture note, so please always look at the latest one. So I correct typo and so on. So please check the latest lecture note. In e-learning. Okay, so then shall we start? Are you ready? There's one correction. The one correction is in here. Sorry. So I missed the I here. To define the time transition, you need an I here. Okay. So I missed that I. Thanks for the pointing out my mistake. So the selection note has a typo here. Okay. So now. So what is the Torres partition function? Pretty ballsy. So now, we just use this definition to compute. We just only look at the only part of the theory. So indeed, Hilbert space is defined by just acting on the creation operator of whatever. To the vacuum. To the vacuum. Okay. As you recall, I think the free bosons are defined is something like a like this one. So as you recall, so you just do the Fourier expansion, and we treat this an is the operator that define creation annihilation, and we call this one is the whatever. Yeah, I think I don't need to use k actually. N1 and so on. That I call it N1, N2, N3, and so on. So this is the how the Hilbert space is spanned. So it's infinite dimension. You can you can access the creation operator a number of times, so that it becomes infinite. And then we need to trace over Hilbert q to L0 minus c over 24. And so we know that the what is the central charge of the free boson? 1. Good. So it should be q to the minus 1 over 24. Okay. And now so we can count the Hilbert space like this way. So you just count the Hilbert space. So sum of all Hilbert space state is something like a Hilbert space. Okay. So now, so we just sum over it. So let's look at the following. So L0 is commute with like a minus k to be k, right? I think as far as I know, yeah, k times a minus k. Okay? So this is computational ratio. Okay? So therefore L0 over let's see, a minus k is 0. Like this way, and you can commute. Then this will give you this the 1. Oh, what I'm doing here? Sorry, so why my up script? It's k. It becomes k. So here you just if you commute. L0 and a minus k, so you get the k times, so let's see, is equal to a minus k L0 plus k a minus k. Okay. And then you just, so this is equal to this one, L0 annihilates the vacuum, and then you just do the computation ratio with the a k and a minus k. Okay. Then you get the k here. You get the k. So therefore, so if you act, so if you only look at the a minus 1 to be some k to be 0, and then L0 a minus k a plus sorry to k sorry, this is n1, right? n1, sorry, n1 0 like this way. And this is also give you the so here once you so this will give you n1. This will give you n1, and you need to sum over. So this one is equal to a minus 1 L0, a minus 1 and 1 minus 1 plus L0. Sorry, A0, a minus 1. And then you can do the number times. Okay, you can number times that will create n1 times a1. Okay, And then you just do the computation between these guys, and then you get the N1. So therefore, if you sum over these states, you will get the if you Q to the L naught N1 0 N1 0. Maybe I should write down sum over N1 is equal to 1 minus Q. You just have a 1 plus Q plus Q squared plus Q to the Q and so on. Okay? So you just count N1. So how many times A minus 1 acts? So this is equal to, by taking geometric series, 1 over 1 minus 2. Okay? So similarly, if you take N2, 0, N2, 0, Q to the L naught, is from, yeah. Is from 1 over 1 minus Q squared and so on. So therefore, if you take the old Hilbert space, trace of Q2, yeah, if you do this one, this will become Q to the minus 24, 1 minus Q, 1 minus Q squared, and 1 minus Q to Q, and so on. And this is equal to, we already know what it is. And this is equal to delicate data function. Okay, so therefore, free bosons, you will have oh, sorry, 1 over 8. So therefore, free bosons, the partition function like this one. Any questions so far? This is a very important point. So now, so we know that the PSA2Z axon Torres is it's mapping class group action modular action that acts on acts on ZB. And in fact, this is not the modular invariant, but so therefore I think I call it election of ZB prime. So the reason is that you have to consider the zero mode of the free bosons. L naught is equal to 1/2 A0 square. And then you can just consider the sum, zero mode sector. So define the so as I mentioned, this can be understood as momentum. So we identified this is pi 0, right? Like last time, free boson phi of whatever w is equal to phi 0 plus, I forgot some constant pi 0, and w bar plus minus, I already forgot. I think plus. It should be plus, right? I think so. Where did I write? Huh? 4.12? Thank you. Yeah, plus. Okay. So this can be understood. The zero mode can be some momentum. Okay. So therefore, vacuum can have some have a momentum indeed. So in fact, maybe some of you guys. So you just consider so Vertex Operator. It's called Vertex Operator alpha. Maybe I will introduce later. E to the essential I alpha in phi. Let's see. So this is called Vertex Operator. I already, you guys do the homework, right? Yeah. That can act on vacuum. That will give you some, so as you can easily see, so this can be understood, so e to the I alpha phi can be understood as some momentum translation in quantum mechanics. So this can, so Vertex Operator acts on vacuum like this way, will give you some infinite family. So the parameterized by alpha of the some states. So therefore, so here we called a zero here. So this is, you can identify, okay, and then alpha. Then you have the following the transformation rule. So this A0 really see this momentum alpha. So that will give you alpha square over 2. And you have to integrate over. It's just Gaussian integral. So that the this will give you so the alpha e to the 2 pi I power 2 alpha square. And this will give you 1 over square root 2 pi 2. So therefore, so you need to, if you include this zero mode contribution, so the partition function can be written as like this way. Can be written. And this is indeed modular invariant. Invariant modular transformation, which means that the ZB, sorry. Okay, so that's the Torres partition function of the free bosons. Now, so this can be understood as the phi as a nonlinear single model. This is called nonlinear single model. So this phi of z, phi of w, whatever you call it, can be understood as the map from Torres to R. So this can be understood map function can be understood is a function or field, whatever. So phi takes the value of R, and then W takes the value of Torus. So it can be understood a map. So now we just compactify it on a circle. So we can consider to S1. Let's go compactify both things. So namely, so if you consider phi of Z then is some integer. So now, so we just consider S1 whose radius is equal to R. Okay. So this is the map called phi W. Phi of Z, whichever color, Z or W, whichever. I mean, whichever color. Okay. So now, so here, so we impose the condition that if you have 2 pi n, you have a periodic condition for any integer n. Okay. So now, so we recall this model expansion pre-bottom. Plus, so this is really model expansion of the free bosons. And anti-home part. So this mode is indeed you have to be careful about this part, zero mode part, because of this condition. So this condition can be understood as phi t, and x plus L is identified phi t of x times winding number. So which means that this whichever color, so this is spatial circle. So this is the x direction, and this is t direction. So if you go around it, so this L, so you just do the n times wrapping. So mapping is something like this. Okay. This is 2 time wrapping, and so this is two time wrapping. Okay. So so this figure is n is equal to 2k. Okay. Okay. So then, so therefore, so you have to be, So if you take x goes to x plus L, you need to have the n time winding, right? 2 pi n. So therefore, so A0 bar is equal to R times n. So in lecture note I use W, but I just try to, yeah, okay, maybe I should use the notation capital W. Because I mean, W is used for coordinates, so maybe let's use capital W in this fraction of the winding number, So therefore, you have the winding. It should, in fact, so it should satisfy this condition. Okay, so this is the winding of C. So winding is so then therefore, if you take the shift x plus L cancel, then you have 2 pi RW. Moreover, so you have the so as I mentioned, as I mentioned, A0 plus A can be understood as the momentum. So this can be understood as momentum, and since the here, so you just have the momentum on a circle. Okay, so therefore momentum on a circle should be quantized. So it has to have the A0 bar. Yeah, should be quantized to n over r. Okay, so the momentum, so if you have the time translation, so momentum is time translation, right? So the momentum is the Fourier analysis of the circle should be quantized by integer, yeah? With the integer. So n is this is winding number. Oh, that's one. Okay. Yeah. So therefore, so vacuum is indeed, or state is indeed. So yeah, vacuum state. I mean, or zero model contribution. You can just have the A0 acts on n and W, capital W, and then A0 bar can be understood. You can solve these two equations. This way, so you can have the state that is labeled by winding and the momentum. So, and so this is equivalent to doing this integral. So here, alpha, as I mentioned, so alpha is now here momentum because R can be, how to say, have a continuous momentum mode. Okay? Momentum. On the other hand, for circle, momentum is quantized. And also, in addition to that, you have a winding mode. So therefore, you have to sum over all the states. Oh, sorry. So this compact line boson radius R can be understood as the sum over n and w, which is integer q to the so you have to sum over all the zero modes. All the zero mode. And in fact, so this is indeed invariant under PSL2Z, which to check this one is the homework. To check this one is homework. And in fact, you have to use so-called Poisson resummation formula. So I'm not going to write down Poisson resummation formula, which is written in the lecture note, but to show this is PSL2Z invariant, which means the is equal to this one is equal to ZR. So this is homework. And as you can easily see, so if you do swap, you can easily swap R to if you swap R goes to 2 over R, the formula is exactly the same. So it becomes 2 n R. Oh, sorry. This becomes this one, and this becomes what I'm writing. What I'm writing. Sorry. So you just swap, I mean, n and w are integers. So therefore, the partition function is invariant under this transformation. Okay. So this is called T duality. So this is called T duality, which exchange the n momentum and winding. So therefore, the theory living on circle R is the same as theory living on other quantum field theory is the same as the what about R? Okay. So this is called T duality. So this is other quantum field theory is equivalent. And then, of course, something special happens when R is equal to 2, square root 2. So then it's called self-dual radius. It's called self-dual radius. So which means if you substitute R equals square root 2, so they are the same. Okay, R square root 2 is 2 over square root 2. So this is self-dual radius, and then we will see later. This is called yeah. I mean, so something special happened. Okay, symmetry enhancement. We will see later. So this is later. So we will see this one this later. Any questions so far? So this is momentum. So therefore, e to the 2 pi I b times radius 2 pi r should, so this is really the translation of space like this one, momentum. So therefore, it should be the same. I mean, time transition p should give you the it becomes should be identity. So p should be quantized by n over r. Any other questions? So we did Torres partition function free bosons. Next is free fermion, of course. Free fermion. Okay, so free fermions, we have mode expansion, and but now you have the frame statistics. So therefore, you can have, so NS sector, you have mode expansion, mode expansion like this way, so therefore you can act the creation operator like this way. Where n k over half is 0 or 1. So it really obeys the Fermi statistics. So that if you have a 2 copy of some whatever, should be 0. Ne? So occupation number is either 0 or 1, and the computation ratio is L0 is given by S is equal to 1/2. Such that the L0 bk is given by k bk. So this is easy to check from this analysis. From just anti-computation ratio. Am I writing correct thing? I think yeah, I am writing correct thing. Okay. Okay. So now, so we just compute the partition function. So we have on the Torres. So Navier-Schwarz, recall that the Navier-Schwarz, so on cylinder you have identified anti-periodic boundary condition. I call it A for anti-periodicity for Nephew ones. Okay. And the fermion, you can also, so if you have one cycle, you can identify, like you can impose either anti-periodic or periodic. Okay. So therefore, we can also impose so suppose we just identify top and bottom of the fermions by up to sign. Okay. So then the character, I call it AA of tau, can be another trace of fermion, so I call it F, Hilbert space to the Q to L0 minus 24, C over 24. Okay. And now, so we know that either, so this, I call it, this one is so if you consider sum over n, okay, then we will have 1, and then we have the plus q. Okay. So 1 is the there nothing, n equal to 0 part, and the q to the 1/2 is the q to the 1/2 is indeed n is equal to 1. Okay. So this is the summation, and the same thing happens. So if you have the 0 and 3/2, and 0 and 3/2, you have this one, okay, and so on. Because of this computation ratio. Oh, what was it? Here. You understand? So if you exchange L0, B K, B minus K, then if you exchange it, so you have minus K, BK, L0, and minus sign, and plus K, B minus K, okay. And then, so of course, you can just make a computational ratio. You get by using this one, you get the constant K. Okay. That will come with the power here. The power here. You agree? So therefore, this can be understood as 1 plus q to the 1/2, 1 plus q to the 3/2, and so on. Okay. This is equal to q to minus. And here, this one is indeed called Jacobi zeta function over A. So it's just definition of the zeta function is given by the following. Did I make that copy? Yeah. Like this way. And it's cut, sorry. And it's cut. Minus, sorry. So, or, yeah. And then if you take the quotient by eta function, you get rid of this one, and then you take square root, you get this one. Any questions so far? So now we change the boundary condition. Periodic. So you can just indeed identify top and bottom by periodic boundary condition, which means the phi, I call it W, W or Z, the W. Is indeed phi W plus tau. So this is periodic, and the anti-periodic is the minus. And this partition function can be understood as follows. Trace of so here I should call NS trace of F and S, but you can identify top and bottom with the sign, so which means the -1 to the F, Q to the L naught. So this -1 to the F is really, if you have permanent top and bottom, it's introduce another minus sign. The minus sign cancel with this minus sign, so you get a plus sign. Okay. That's what's going to, and F is called permanent number. And the computation is exactly almost same as before, and here you have the you have to just do the computation ratio between permanent operator. This is equal to indeed. So what I meant is the computation ratio here will give you minus. Okay. Okay. And if you commute this one, so FC this creation operator or annihilation mode of parametric mode, so that you get the sign. This will equal to BR -1 to the F is equal to negative sign here, and plus BR -1 to the F, so therefore this is equal to 0. Okay. Okay. So therefore, computation almost same, but now here, so we need to insert P here. So if it is here, so you need to insert negative sign here. So you have a negative sign here. Since so here we insert -1 to the f, and we sandwich by -1 to the f, and if you need to how to say, commute bk and the -1 to the f. Okay, -1 if there is a Fermat mode. So therefore, essentially what you get is 1 minus this one, okay, instead of 1 plus. And this is equal to square root theta 4 tau. Namely, theta 4 is defined as the theta 4 here is minus sign. Good. Now, as you can easily see, so theta 3 is this, okay, maybe 3 and 4 is plus or minus here. Okay? And this, so Q is, we know, 2 by I tau. And if you shift tau to tau plus 1, by T transformation, this plus 1 shift will C times this odd integer will give you another minus sign. 2 by I divided by half integer is -1. Okay? Therefore, plus minus up to this T transformation, plus minus will be swapped. Okay? So therefore, so they are related by T transformation. Okay? Like this. And that can be easily see that the indeed from a geometry. So antiperiodic means the minus sign, antiperiodic minus sign. And if you do T transformation, you get this torus. And since minus times minus is plus, it becomes, this is periodic. It becomes periodic. -1 times -1. If you do the T transformation, the tau goes to tau plus 1. A goes to antiperiodic becomes periodic. Okay? So therefore, this makes sense. This makes sense. Likewise, if you do the T transformation, -1 times P is -1 times plus 1 is -1. Therefore, becomes A transformation, antiperiodic condition. Okay, you understand? -1 times P, -1 times 1 becomes -1. Okay? Therefore, so this transformation really makes sense geometrically. Any questions so far? Oh yeah. And I have to say that the so we learn T transformation. We learn T transformation, and the PSI2Z really generated by T and S. Okay, T matrix and S matrix. So we can ask the same question: what happened S transformation? S transformation essentially swap spatial direction tau goes to -/tau is essentially alpha 1. I call it alpha 2, alpha 1. is swapped to alpha 1, alpha 2. Okay? So therefore, two vector is swapped S transformation by S transformation. You understand? So therefore, it's anti-periodic becomes anti-periodic. I mean, both anti-periodic, which means this guy is invariant to the S transformation. Okay? Since this is the anti-periodic, even if you swap the same boundaries. On the other hand, here something wrong, something different will happen. If you do this S transformation, if you swap anti-periodic and periodic, what you get is by S transformation. You get the periodic, anti-periodic. Okay? So we need to consider new guy, okay, to see what's going to happen under S transformation. Okay? Okay, so we will see. So now, we want to see the following guy: periodic, anti-periodic. So now we need to consider the following. What should I do? So computation almost parallel. So this character, I call it so I call it this one is chi PA. So now we need to consider chi AP. Yep. So that will give you the almost same transformation, but how do it go? So let's do the same computation. So trace of Fermat. Now you have a Ramon instead of and the Q to the L0 minus C over 24. And now, so as you recall, this minus 1 over 48 is vacuum energy for vacuum. Okay. So now, it becomes for Ramon sector 1 over 24. It becomes 1 over 24 for vacuum. Okay. And then we have 1 plus Q. 1 plus Q squared, and 1 plus Q to the cube, and so on. So now, mode expansion K is instead of half integer, it's now integer. Okay. So for Ramon sector. So as you recall, so psi of Z is something like a BK, Z to the minus K minus 1/2. K is the Z plus nu. When nu is equal to 1/2, you have a Levy Schwartz, and then nu equals 0, you get the Ramon. So therefore, it's a integer mode now. So instead of half integer over there, so we have an integer here. Okay? And you have to be careful about the overall sign, overall factor. So here you have to use I think this square root 2 really come from I think this is indeed multiplied by square root 2. The reason is that it should come from zero mode. Did I write the computation for square root 2 in the lecture note? I think presumably no. So why do I have the square root 2? So if you have a vacuum, you can also define, I think it's just normalization. It's just normalization. And also you can have a zero mode axiom like this way. You have two states. So the vacuum, and so psi 0 can act on vacuum. And then I just confused by the point. I think psi 0, anti-computation ratio will give you 1, right? I think 1. And then psi 0 square is equal to 1. So 2 times, yeah. So therefore, and then we are close to square root 2. So therefore, square root psi 0 square is equal to 1. Oh, am I writing correct thing? No, right? I'm not writing correct thing. It should be 0, right? Sorry. Why? You guys should. That's why you guys are laughing? So, yeah, this is correct. And then, I don't remember. Why do I get the square root 2? It should come from some zero mode. But I already forget why I need to have the square root 2. I already forgot. I think last semester I taught string theory, and the string theory course I clearly explained where the square root come from, but I already forgot. Okay, so next time. Okay, I will explain next time. So it's better not to spend waste my time. Waste your time. So next time. Why? I think it should come from this zero mode. I already forgot how I did that. I cannot remember. Yeah, I cannot remember. Yeah. What? Do you remember? What? Okay, so I don't. So, and then, so you can check that the so this is chi PA. So the S transformation swap is two cycle here, 2 1 cycle. So you get the following relation. Therefore, so by S transformation, like this way, okay? So what about how does t act on? So that can be easily seen from geometry. So as I mentioned, so this +1, -1, if you multiply them together, you get the -1. So you still have, by t transformation, you just have A. So therefore, this should have invariant t transformation. So this is already given. So this transformation rule already found by Jacobi, and this theta is called Jacobi theta function. And then so in total, so if you sum them up, Fermion Torres partition function is you have to introduce all the So one can answer the following question. Sorry. So periodic boundary condition. So this is the trace from Q to L0 Hilbert space, and this is indeed 0. So the reason is, do you understand why this is 0? So you have take all the Hilbert space F periodic. Yeah. So you need to sum over Q to the L0 minus 1 to the F, and sum of vacuum. And plus Q to L0, like this way. Okay. And now, so 0 mode, just swap, you get a minus sign. So if you swap like this way, you get a minus sign. Okay. And the psi 0 and the L0 is anti-commute. So which means the what's the computational ratio? Yeah, this one. So if you plug in 0, it's the same as vacuum. It's like vacuum energy. So 0, you get 0. So therefore this will give you 1, and this is give you minus 1. Okay. So this is 0. Okay. And you can act to many things. So you can act to whatever psi, whatever minus k. You can act at psi minus k, psi k, and psi k. Always, if you have a 0 mode, or you always have minus sign, and the energy is the same. So always there's a pairing between psi minus k and psi minus k psi 0. Okay, you understand? So then always signs are different, but the power of L0 is the same, okay, due to this computational ratio. Okay. So therefore this is 0. So now under the all, so you have to sum over all the boundary condition on periodic, anti-periodic. So for and you have 1/2. due to the overcounting of n sector. So here, so this coming from for AA, PA, and then AP, right? AP. Okay. And so since you have two n sector, so you have to divide it by 1. So this is sum over all boundary condition. So this is the sum over all boundary condition. Or how to say? Yeah, boundary condition or periodicity or periodicity. All the periodicity, okay? And this is indeed modular invariant. And in fact, moreover, this is indeed equal to 0. If you sum them over, am I correct? As far as I remember, this is indeed. Am I correct or wrong? I think I'm wrong. So this is not 0. Sorry. So if you have the 10-dimensional space, yeah. If string theory, if it is string theory, you have a power to the fourth, and then it becomes the 0. But this is okay. Any questions? I think it's good time to stop. And next time we'll move on to the minimum, the most important family of 2D CFT called minimum model. Any question? Okay.